Hello everyone, it's a pleasure to introduce our research titled Electronic Properties and Molecular Electrostatic Potential Mapping of Graphene Quantum Dots Decorated with Zinc Oxide, Copper Oxide and Titanium Dioxide with authors Dr. Hend Ezzat, Professor Hanan Al-Hayes and Professor Medhat Ibrahim. Let's start with our overview. Consisted of introduction, computational details, building model molecule, HOMO-LOMO orbital distribution, molecular electrostatic potential, and finally our conclusion. Firstly, we will introduce our work. Graphene quantum dots are nanometer-sized fragments of graphene which fabricated by fragmentation or cutting of graphene sheets. Cutting graphene sheets into small clusters produced graphene quantum dots with different shape and edges. Energy gap strongly depends on shape, hexagonal and triangular, edges, termination, zigzag and armature, and size of the graphene quantum dots. Graphene quantum dots have been widely studied in recent years due to its unique structure, related properties such as optical, electrical, and optoelectrical properties. Graphene quantum dots are considered a new kind of quantum dots as they are chemically and physically stable because of its intrinsic inert carbon property. Furthermore, graphene quantum dots are environment friendly due to its non-toxic and biologically inert properties. Functionalization of graphene quantum dots has the potential to modify electronic properties and enhance optical properties of quantum yields. So our computational details, graphene quantum dots in 4 different forms interacted with metal oxides such as zinc oxide, copper oxide, and titanium dioxide following the density function theory at B3 lab plan L2DZ calculations. Models processed using Gaussian 09 software, HOMO-LOMO orbital distribution and molecular electrostatic mapping were conducted for model structures to investigate electronic properties. To study the effect of decorated graphene quantum dots with metal oxides, we build our models as graphene quantum dot with different shapes, hexagonal and triangular, with 2 forms, zigzag and armature. Interacted with metal oxides such as zinc oxide, copper oxide and titanium dioxide, once from oxygen atom and once from metal atom. All model structure conducted to calculate HOMO-LOMO bandgap energy and molecular electrostatic potential to study its electronic properties. For graphene quantum dot armature hexagonal form, metal oxide changed the orbital distribution and the color map of molecular electrostatic potential, which increased the reactivity of graphene quantum dot surface. Also, total dipole moment increased while band gap decreased with decorated graphene quantum dot with metal oxide. And the most enhancing metal is titanium dioxide with band gap equal 0.3. In the case of graphene quantum dot zigzag hexagonal, metal oxide changed the orbital distribution and the color map of molecular electrostatic potential also changed with increasing in red color, which increased the reactivity of graphene quantum dot surface. Also, total dipole moment increased while band gap decreased with decorated graphene quantum dot with metal oxide, and the most enhanced metal is titanium dioxide with band gap equal 0.5. Also, in case of graphene quantum dot with armature triangle shape, orbital distribution and the color map of molecular electrostatic potential of the structure were changed, and the reactivity of quantum dot surface also changed. The total dipole moment increased while the band gap decreased and the most enhanced metal oxide was titanium dioxide with band gap equal 0.2 electron volt. Finally, in the case of graphene quantum dot zigzag triangle form, metal oxide changed the orbital distribution and the color map of molecular electrostatic potential, which increased the reactivity of graphene quantum dot surface. Also, total dipole moment increased and band gap energy decreased with metal oxides, and the most enhanced metal oxide was titanium dioxide with band gap equal 0.25. So we can conclude our work that adding metal oxides increases the total dipole moment while decreasing the band gap energy of graphene quantum dots with different forms. The most effective metal oxide on graphene quantum dot was titanium dioxide that enhanced band gap energy, and the most enhanced structure was graphene quantum dot zigzag triangle form with titanium dioxide nanoparticle. Accordingly, graphene quantum dots seem to be excellent for different nano device applications such as sensors due to their increased responsiveness and energy gap variation. Thanks a lot for your attention, and I am waiting for any questions.